I am Arjit Sahu. I am a PhD student at Chennai Mathematical Institute and TCG Crest on building a scalable bit vector model counter. And this is a joint work with my PhD advisor, Dr. Kuldeep Singh Mill. So today we'll start by dissecting the title of the talk. So what is a model counter? So given a formula, the problem of model counting is to count the number of satisfying assignments of that formula. So we call the satisfying assignment as a model. So counting the number of satisfying assignments is the problem of model counting. So let's put in the context of SAT-SMT. Given a formula, if you want to know the solution of satisfiability, you have this SAT or SMT solvers. And if you want to know the number of models, you have these model counters. And the last few years, like last few decades, have seen a significant improvement in the performance of these model counters, both approximate and exact model counters. But the question is, who needs a model counter? It turns out lots of people need a model counter. And here is an example. So like these are few research papers that has been published in last few years that comes from very different domains. So they are from computational biology, cryptography, software model checking, machine learning, neural networks, and so on. And these all are reduced to the problem of model counting. And all these applications that inspires us to make even more better model counter. So if we look closely at some of these instances, we will get to know something more. For example, on this work on software model checking, they were reducing this problem of software reliability to the problem of model counting. And in this process, they were using CBMC. And they were asking CBMC to emit a CNF, which they were using a propositional model counter to count that CNF. In this work on cryptography, they were using G3 to encode their model, and they were asking G3 to emit a CNF. But if this problem was not of model counting, and if this problem was of satisfiability instead, they wouldn't have used this SAT. They would have used SMT encoding. Why so? Because SMT is more efficient in encoding things. But they haven't used SMT here because there is no such good SMT counters out there. So in these two and some more of these applications, they come from a SMT theory called bit vectors. So the problem today that we are focusing now is of bit vector model counting. So what is a bit vector? A bit vector is essentially a vector of bits. And in the theory of bit vectors, you can do all kinds of operations on these bit vectors that you can add them, multiply them, subtract them, rotate them, and so on. And why this bit vector counting is interesting? Let's have an example. So here is an example where each x1 to x10 all are 32-bit bit vectors, and we have these constraints that says like x1 equals 0, and x1 is less than equals x2, x2 less than equals x3, and so on. And there is a final constraint that says x10 is less than equals x1. So by the time I have said it, you have probably figured out that the number of solutions for this set of constraints is 1, and that is that everything you need to set to 0. So at this last moment, you have made a reasoning over 320 bits. That is not very simple, but if we have some smart bit vector counters that can reason this smart. So what is the current state of the art in the context of bit vector model counting? So there was a work from 2016 that is called SMT approximation that gives an approximation of bit vector formulas, and that gives that approximation with some theoretical bounds. There was another work that is called SearchMC that came in 2018 that scales well but doesn't give such kind of guarantees. And always you have this third option to bit blast the formula or reduce this bit vector formula to a Boolean formula and use these propositional model counters to count that Boolean formula. So while we were searching for benchmarks, we came across this CAP 21 paper. That was also from software model checking, and they were working on this problem of robust reachability. And they had two definitions of their problem. One was this quality, for which they were using satisfiability, and they had another definition of robust reachability that was using some quantitative definitions. And for that quantitative definition, they were reducing their problem to bit vector model counting. And in this process, they used these first two model counters, SMT approximation and search MC, and found out that none of them scales on their problems. And after that, they concluded that like their definition with quantitative reasoning, that is not that scalable. So that was indeed a challenge to us. So we looked at their problems and we found, so we know that the search MC and SMT approximation, none of them scales. So at that time, we are working with some propositional model counter that is called SMT approximation. So that is called ADDMC. So we reduced the problem to a CNF formula and used ADDMC. And to our surprise, it turns out that all of the 92 instances that got solved in 1 second. Like each of them was solved in 1 second. That was quite a surprise to us, because if this result was known to the authors, they would have concluded completely differently about their encoding to bit vector model counting. So we took up this research question that what is the, given a bit vector formula, what should be the best way to model count that bit vector formula? And for that, we chose the third way to bit blast that formula and use this model count, propositional model counting techniques. So we designed a portfolio system that is called SARP SMT that has 3 components, and that works in this way, that given a bit vector formula, it uses some bit blasting technique to convert it to CNF. Then it uses some preprocessors to simplify that CNF. Now, to count that simplified CNF, they uses this SARP SMT uses a propositional model counter. So I'll be talking, so there are many techniques available for each of these steps. So I'll be talking very shortly about all of them. So this bit blasting is the procedure of converting the process, a bit vector to a CNF formula. And this is quite common in the SMT solvers. So given a bit vector formula, the SMT solvers generally reduce it to an AIG, that is an AND inverter graph. And then this AND inverter graph is converted to an CNF using this site-in encoding, that is quite common. There was another technique that came in 2007 that is called technology mapping-based logic synthesis. So in this technique, they makes a compressed circuit out of this AND inverter graph. And for this compact circuit, they make a compact CNF. So this CNF made using this technology mapping-based method is smaller than site-in encoding. But in case of satisfiability, it has been shown that it is not always helpful. Like in many of the cases, this site-in encoding is quite more efficient than this technology mapping. The next thing we will be discussing about is preprocessors. So given a CNF formula, the task of a model counter is to give a model count. The task of a preprocessor is to make this CNF simpler, so that that simplified CNF should be easier for a model counter to count. And it has been shown that there are a few preprocessors which perform quite well in terms of this model counting. Like this, there is this preprocessors called B+C and Arjun. So they perform quite well while used for model counting. The last thing we have is propositional model counters. So there are quite a lot of propositional model counters, and as I told that like last 2 decades has seen as various and very significant improvement of these propositional model counters. So we picked up 5 of them, which are not only shown very good performance in the last model counting competitions, but also they have very different techniques. So these first 4 counters, they are exact counters. That is, like given a formula that gives the exact model count. The last one, this approximation, is an approximate model counter. So that gives an count with some epsilon and delta guarantees. That is, we have some error bound and some tolerance bound on the count. So with all this, we have two different deep clustering techniques. We have 2 preprocessing techniques. We have one more option to not preprocess an instance at all. And we have 5 different model counting techniques. So we have 30 different possibilities in which we can run our portfolio SARP SMT. And to know which one is the best, and also to know the impact of the different components, we did experiments, and for that we curated a benchmark set for which we took benchmarks from cryptography, software model checking, and some from older literature. And we have a benchmark set of 679 benchmarks. With all those, we did our experiments, and here are the results. So the first thing we compare is the impact of different model counters. So the first thing, this is a bar plot, and like in this x-axis we have the number of all the benchmarks that are solved within 1 hour of timeout. So we have 679 benchmarks, and this SMT approximation, the current state of the art, can solve only 135 of all the instances. So we then bit blasted those instances with cytine encoding. We did no pre-processing, and we found out that this exact model counter, subset TD, that performs quite well. Like that solves like 412 instances, which is like almost 3 times of the current state of the art. Surprisingly, this approximate model counter, approximation, that performs quite well in this model counting competition, that was not that efficient in our case. The next thing we compare is this bit blasting techniques. So we have 2 bit blasting techniques, this cytine encoding and technology mapping. So these red lines that represents the instances where bit blasted using cytine encoding. The blue ones represent that the instances were bit blasted by technology mapping. And it is quite evident that this cytine encoding is better in all of the cases. Like for all of the cases, cytine encoding performs better than this technology mapping based bit blasting. The third thing we compare is this pre-processing techniques. So here this red line represents the instances were not pre-processed at all. The blue line represents that was bit blasted, that was pre-processed with B plus E. And the yellow line represents that the instance were pre-processed with Arjun. And for the exact model counters, it is shown that like these preprocessors are not that helpful. But in case of this approximate model counter, its approximation, this preprocessor has helped a lot. Like with preprocessing with Arjun, this approximation can solve 492 instances, which is better than any previous setting. So at this behavior, the same behavior was shown, a similar behavior was shown, like this previous one was encoded by cytine encoding, and when we bit blast the instance with technology mapping, a similar behavior was shown. But in all of the cases, this technology mapping was not that good a performer in comparison to cytine encoding. So at this point, who are the winners? It turns out that if you want to know that if you are happy with approximate model counting, you have to encode the instance using cytine encoding. Then you have to bit blast with, you have to preprocess with Arjun, and you have to model count with approximation. If you need exact model count, then you need no preprocessing. You have to just bit blast the instance using cytine encoding, and you can use this model counter subset TD. So at this point, we are doing good, but still we are missing something. So these preprocessors, B plus E and Arjun, they perform, like they behave quite similar in some cases, but they have different strategies in many of the cases also. So we thought of using a new combination, like we'll use B plus C and Arjun serially. Like we'll preprocess an instance both with B plus C and we'll preprocess them up with Arjun. So at this point, we do not have 30 possibilities, we have 40 possibilities. And it turns out that this B plus C plus Arjun preprocessing has helped a lot. And at this setting, if we are blasting the instance with technology mapping, this setting can help approximately to solve 617 benchmarks, which is more than 90% of these benchmarks. And there are two more interesting observations here. One is that this technology mapping based encoding was not a good performer earlier in any of the settings, but in this case, that has helped to solve most of the instances. And the second observation was these two preprocessors that we have used together, that was generally not recommended in any of the settings. Like when this Arjun was published, they said that Arjun should be used in place of B plus C. So to conclude, we have explored all the possible options. Like we have explored all the 41 possible options to model count a bit vector formula. And out of these possible options, we have found out which one are the best possible settings. And that should make life easier for people from many different domains who can encode their instances to bit vector model counting. For them, our portfolio system SARP SMT can work like a bridge among these practitioners, like developers and users of bit vector model counting. And for them, this should be a helpful thing. And this code for our portfolio SARP SMT is available online. You should give it a try. And thank you for your attention. If you have some benchmarks that is useful in this context, please share it with us. Thank you.
Time for one quick question. Yeah.
Hi, Arijit. Thank you for the great talk. I had a question about the sharp-set TD. Can you give us an intuition why with the pre-processing sharp-set TD's performance degrade? That's what it is.
I can say like why it hasn't improved that much. Like this approx MC can use like this. So let me go to this slide, and I have an extra slide. So if you look at the instances, and these bit vectors are converted to AIG, as I was saying, and then this AIG is converted to CNF, and as AIG is a kind of a circuit. So in the circuit, you can see, like for this example in this circuit, you can see that if you set these values for V1, V2, and V3, all the remaining variables are determined by these variables. So if you can extract that these three variables are responsible for all of them, then it is enough to count only on these variables. Like if you get a count of this, you can get a count for all of them. So that is the thing that these preprocessors can generate. Like these preprocessors, B plus C and Arjun can get this thing out of a CNF, even if this circuit is not given to you. So this is called a projection set, and this projection set is extracted by these preprocessors. So these preprocessors, this projection set is usable by approx MC. That is why that has helped a lot, but that is not usable by other model counters that much. So that is why it hasn't helped.
Okay, in the interest of time, let's thank Arijit and